Hello, my name is Daniel Houston, and this is my Lab 4, Circuits and Capacitors. Throughout this lab, we're going to look at various circuits and capacitors and see how they're affected when the components are manipulated around them. In this lab, we're going to need a few equations. First, we're going to have Ohm's law, which is just delta V equals IR. And then we have the loop rule and the node rule. And then we're also going to have this equation to solve for the time constant using the natural log of the potential difference over the potential difference delta V naught equals negative T over the time constant RC. For our procedures and observations, we're going to use this simple circuit that we have right here. It's a series circuit that has two 1.5 volt batteries and has two ammeters, both at I1 and I2, and then two resistors, one at 47 ohms and the other at 100 ohms. And then at I1, the value of the current measured is the same as the value for I2, which are both known to be 0.02 amps. And when the ammeter is backwards, the value for the current does not change. And also, when the ammeter is replaced with the voltmeter, I equals 0.02 amps, and then delta V equals 3 volts. Looking at this picture here, we can see many of the potential differences between several points around this circuit. First being, if you place it around the battery, the potential difference will be 3 volts. And then if you place the voltmeter cords around the 47 ohm resistor, you'll get actually a value of negative 0.096 volts. And same for the 100 ohm resistor, you'll get negative 2.04 volts. And then the sum of the potential differences around this whole circuit will be 0. And this graph shows the changes in potential differences from the battery to the resistors and to the ammeter. Now, when we're looking at a parallel circuit, we can see that a voltmeter still does not affect the current, and the ammeter would still read 0.02 amps whenever a voltmeter is placed. And in the same parallel circuit, if you place an ammeter, as seen in the top left corner, you'll get a value of the current to be 0.06 amps. But if you change this ammeter to a 100 ohm resistor that's parallel to the 100 ohm resistor, the amp will change to 0.03 amps, which is seen in the bottom right corner. And working backwards using the potential difference and the value for I, we can calculate the resistance for each of the components. First being the 47 ohm resistor, and you can see the 0.96 divided by 0.2 will approximately equal 47 ohms, which is the value for the resistor, and same goes for the 100 ohm resistor. And then additionally, for the wire and the ammeter, you can also see that there's 0 potential difference, which would mean there's 0 resistance in this ideal case. Now, in our new RC circuit, there's a few things to note before we proceed. First being, the battery voltage will change to 9 volts, and then we're going to add a light bulb and a capacitor. And the light bulb will have a resistance of 10 ohms, and so when connected to the battery, the light starts bright and then becomes dull as the capacitor charges. However, when the battery is disconnected and the circuit is still connected, the light again starts and then becomes dull as the capacitor discharges. And then whenever the capacitor is charging and discharging, the current starts large and then decreases. And this is the charge and the discharge time of each of the light bulbs used. And over a 20-second period, this is the graph for the potential differences versus the time of a 30 ohm resistor light bulb. And then this is the natural log of the potential difference over the original value versus time. And this is the value we got for the time constant, which is -1 over the slope from the line seen previously. and we got to be a value of 5.285, which is very close to the actual value. Now, if you were to do this lab in real life and use an actual ammeter instead of a simulated, this would change because it would measure a lower current because a real ammeter has resistance while an ideal ammeter has no resistance. Also, if we were to simulate this model in real life, it would take longer than our ideal model because all components have resistance to them.